Hello everyone. Our today's topic is this optical activity, and to understand this, first we'll start with ordinary light whose waves vibrate in all direction. This is, as I said, ordinary light. So when this is passed through Nichols prism, a beam of light emerges out, and that is known as plane polarized light. The important thing here is the waves of plane polarized light vibrate in one plane only, as you see here. And such light is when passed through any organic substance. So the property of this organic substance is it can rotate the plane of plane polarized light towards left, that you can see here, or right. If an organic substance which can rotate the plane of plane polarized light to right hand side or left hand side, it is said that the given substance is optically active. Organic substance will be called optically active, and this substance can also be called on the basis of rotation. If it rotates towards right side, then the substance is known as dextro-rotatory substance, and if it rotates left hand side, it is known as levorotatory substance. And suppose if a substance is given which does not rotate the plane of plane polarized light, then it is said that it is optically inactive. Okay, so now we'll see that to become optically active, what is very important is the substance which is optically active must contain asymmetric carbon atom or chiral carbon atom. This is must. Now what is chiral carbon atom? So to understand this, we'll see. Like if there's a carbon to which 4 different groups are attached, such carbon is known as chiral carbon. For example, like as we see here, this carbon here is chiral carbon, and we denote it by putting star mark or asterisk mark. This is asymmetric carbon atom, and it is must, it should be there in that organic compound. And why this is known as chiral carbon? Because this carbon is bonded to 4 different atom or group of atoms. If a given substance does not contain chiral carbon, so it cannot rotate plane polarized light. For example, suppose if we have this, first I'll write plane polarized light is when passed through For example, if we have ethanol, CH3, CH2OH. So ethanol cannot rotate the plane of plane polarized light. Now we'll see. As I gave explanation, we'll just see by this picture diagram here. No rotation. And that's why it is said that alcohol is optically inactive. And why this alcohol does not rotate this plane? Because it does not contain chiral carbon atom. Okay, so now we'll see that dextro and levorotatory, if together we have a mixture of two, then that is known as racemic mixture. What is this racemic mixture? Suppose if I have lactic acid is of two types, D-lactic acid, or we write plus lactic acid. Another is L or minus lactic acid. We'll do this racemic mixture. That means the mixture of two means dextrolactic acid and levolactic acid together. That is known as racemic mixture. I'll just show this and then we'll go for enantiomer. Exactly, I'll explain why this lactic acid is dextro and levo both. But before going to that, just see this, what is racemic mixture here? That is optically inactive. Means if I have this plane polarized light, which is when passed through racemic mixture, and this racemic mixture is of lactic acid, it contains both in equal amount equimolar dextro and levo lactic acid together. So what we observe actually, we see that the plane of plane polarized light remains as it is, means there is no rotation, and hence it is said that racemic mixture is optically inactive. And how it happened here? Due to external compensation. But now some of the students might be thinking, sir, what is this lactic acid? Why this dextro and levo? Okay, I'll go for that. I'll show you that what is exactly it. The meaning is enantiomer actually. This we have to see. Enantiomer is nothing but optical isomers. Okay. Now we'll see what is this. Say, for example, we'll go for our that topic, lactic acid. So the structure of lactic acid first we'll see. Even we can say here the topic is optical activity of lactic acid. So the structure of lactic acid is, here we have OH group, carboxyl group, here methyl is there, and hydrogen. So lactic acid is optically active because it contains one chiral carbon atom. As you can see here, this. Okay, now it is said that there is a formula A equals to 2 raised to n. A for number of isomers, and your n is number of chiral carbon atoms. And as you see here, lactic acid contains only one carbon atom. That's why the number of isomers possible is 2. For lactic acid, two isomers are possible, and that two isomers are, one is dextrorotatory, other is levorotatory. And that's why, as you see here, I wrote this D-lactic acid, because dextrolactic acid is denoted by small d or plus sign, and levo is represented by letter small l or negative. Now we'll see the structure of that. Okay, first of all, suppose if you want to understand that this given structure is dextro or levo, because then only I will write two isomers. First you see this, then I'll write that. Without help of light, even we can find out this optical activity, means if it is dextrorotatory or levorotatory. How to do that? Okay, we'll see this. So what you have to do is, you have, out of all four groups or atom or group of atoms which are attached to carbon, you have to find out priority, which one is bulkier group here. So the bulkier group is OH, because the atomic number of oxygen is 8, and second number is carboxyl group, third is methyl group. So now what you have to do is, you have to see the rotation. Rotation in the sense how this 1, 2, 3 moves. If you see 1, 2, 3, see this, it is moving anti-clockwise. So what you have to answer here is, this is dextrorotatory. Why dextrorotatory? Because what you have to do is, before answering this rotation, you have to check number 4. Where is this number 4 present? If it is present at left side or right side, then configuration you have to change. Means, as you see in this, it's moving anti-clockwise, left hand side. So you have to change your answer. You have to say the given substance is dextrorotatory. Okay, if this is dextro, now what I will do, I will write that to enantiomer. See the enantiomer which I'll write here. Carboxyl group is this. Here is OH group. CS3 is here. This is H. Okay, now I'll write mirror image of this. So that is a carboxyl group here. C, this OH, and here H, and this CS3. Means it is said that, as just now we find out this structure number 1 is dextro, means 100% structure number 2 will be levo. So this is D-lactic acid, and the next is L-lactic acid. So these two are called enantiomer. They are optical isomers. This pair, number 1 and 2, if number 1 is dextro, second number will be levo. And about this only I was saying, like together, if we take a mixture of both, that is known as racemic mixture, which is optically inactive. Now, as I showed you here how to find out this optical activity, even we can say, better to say configuration, how to find out if this is dextro or levorotatory. We'll have more examples here to make you understand the given substances dextrorotatory or levorotatory. And even that concept is known as RS configuration. Just we'll see this, we'll have a look on this, what is RS configuration. So meaning of R is rectus, which means right, and S is sinister, the meaning is left. Even this RS configuration, in simple way, you can understand this dextrorotatory and this levorotatory. Okay, so we'll have one example here to make you understand more. The example is, suppose if we have this CHO here, and top we have carboxyl group, bottom if I have CH2OH, and here we have, for example, as H. Now we want to find out if this given organic compound is dextrorotatory, levo, or you can say this is having R configuration or S. This R belongs to this dextro. Okay. Generally what happens, if the rotation which we get, if it moves towards right hand side or clockwise, it is said dextrorotatory, and the configuration is R configuration. Okay, so now we'll see what we are getting in this case. But the problem is what here is, we have carbons in 6, 6, 6. Now how to find out which group is bulkier group, which comes first in priority series? जो group बड़ा है ना, that should get number 1. So how we'll decide that? Okay, we'll see here. For example, you have C double bond OH. This can be written like O, and even I can write O down here, and H. Out of 2 oxygen, one is known as a phantom here. So for carbon, we put 6, and this carbon is bonded to 8, 8, 1, 8, 8, 1. Okay. Now we'll say this for carboxyl. Carboxyl is C double bond OOH. We can write it like oxygen up, as double bond is there. One is phantom here, other is oxygen here, OH. So for carbon, what you'll write? For carbon, we'll write 6, and this 6 is bonded to, as you can see here, 8, 8, 8. So we'll write 8, 8, 8. So you have to compare this 8, 8, 1, 8, 8, 8. So you'll get that carboxyl gets number 1 and CHO gets number 2. Then obviously this CH2OH will get number 3. First, what you have to do is, you have to assign here number 1, 2, 3. Now see this rotation. If you'll see the rotation here, 1, 2, 3, how it moves. Clockwise. See, right hand side, clockwise, dextro, R configuration. But our final answer is, this compound is levorotatory and having S configuration. Why like this? For this, I said earlier, what you have to keep in mind is this number 4. The position of number 4 decides actual configuration. If number 4 is present at left or right side, then whichever configuration or rotation you are getting, you have to reverse that. As we are getting clockwise, right hand side rotation, but the final answer which we are giving is levorotatory S configuration. Even though for that CH2H, even I didn't write here, so I'll write for CH2OH also to make you more understand this. In case of CH2H, it is H up, H down, and here is OH. So what we'll write for this? As carbon is 6, it is attached to 8, 1, 1. You can see here 8 oxidation number, sorry, not number, atomic number 8. Then here we have 1, here we have 1. Okay, now we'll see one more example to make you more understand this. Suppose if example is, here we have cyanide group. So this is H, and this side we have CH3, and here we have OH. So how to find out? Now we can say configuration and that rotation. Okay, so for cyanide what we can do is, cyanide is C triple bond N, so we can write here carbon is 6, and this 6 is bonded to 7, 7, 7. How come this? Say this 7 here. Say I'll write it up. Say here, for to understand this, I'll put C and this. See in this all now, you can say phantom here is so this carbon 6 is bonded to 7, 7, 7. Okay. And OH, you know, that starts with atomic number is 8. Bulkier one is that. So we'll put number 1 here. Second number is cyanide. Third number is this. About methyl, if you want to see, methyl is carbon bonded to hydrogen, hydrogen, hydrogen. So what we can write for this? For this we can write 6 is bonded to 1, 1, 1. Okay, so finally this is decided now. 1, 2, 3 we got here. Now we'll see the rotation. So rotation 1, 2, 3. See this 1, 2, 3, how it moves. Again we are getting clockwise. When we get clockwise, what I said for clockwise, I said dextro and R configuration. So this time the answer will remain same, will not change. See what we did in this case. We were getting right side. But final answer what we gave here, see reverse of that. But in this case, it will remain as it is. Means this given compound is dextrorotatory and having R configuration. Why? Why like this? Because see this number 4 is present at bottom. If it is present at bottom or top, whatever answer, whatever configuration you get, that remains same. You don't have to change. So this was all about, you know, this without help of plane polarized light. Even this is the method to find out dextrorotatory, levorotatory substance. And here, this which I wrote was enantiomer. And how we decided this? On the basis of number of chiral carbon atoms present. If any, say one more line I just want to add. any compound, if it is having chiral carbon atom, so it will show isomerism. For example, if we have a structure, say glucose, CHO and CH2OH here. Number 3 we have OH left, rest all we have right side. This is the structure of glucose, D-glucose. This D is, the meaning is different. It's not dextrorotatory. This you will understand more in biomolecules chapter. So here I want to discuss with you how many chiral carbons are present in this. So in glucose, 1, 2, 3, 4. 4 chiral carbon atoms are present. If there are 4 chiral carbon atoms, so how many isomers are possible for this? So formula is A equals to 2 raised to n, A equals to 2 raised to 4, so A equals to 16. So for glucose, 16 isomers are possible. Out of 16, 8 are dextrorotatory and rest 8 are levorotatory. So this way we find out enantiomer, optical isomers. The formula is given here. So for the day, this optical activity part is done. Thank you very much.